Let's take a look at a complete walkthrough of solutions to the second free response question on the 2024 AP Calculus A/B exam. And this is a calculator active problem, so make sure you have your calculator handy so you can follow along. And we're actually going to use our calculator in every single part of the problem, which doesn't happen that often. So it's pretty heavy calculator use. Not only that, this problem is all about motion of a particle along the x-axis, which is a classic AP-style problem, so it's a great one for us to be practicing. Let's dive in. So, as I said, this problem is all about motion along the x-axis, and we're really not given that much information at all. We're just told that for t greater than or equal to 0, the velocity of the particle is given by this function. And we're going to go wham bam through parts A to D and figure out a lot of what this particle is doing. So in part A, we are asked to find the time between t equals 0 and t equals 2 when the particle is at rest. So at rest, remember, just means we want to solve for when the velocity is 0. This velocity function looks pretty nasty. I'm not necessarily sure how it would solve that algebraically. So it's pretty good. I have my calculator. Let me pull up my calculator app and we'll get started. So I'm going to jump into the y-equals menu because I'm going to solve this equation by finding the x-intercept of this graph between 0 and 2. So I'm going to type in the rule. It is natural log of the variable squared, I'm using x, you should probably use x too, minus 4x plus 5, and then I am going to, subtract 0.2 times my variable. Now notice we want t to be between 0 and 2, so I may as well restrict my window so I don't accidentally get distracted. So I'll change my x min to be 0 and my x max to be 2 under the window, and now I can just hit graph and see what is going on. If I do this on my physical calculator, you can see this is what I get. This is probably what you'll get to if you're working with a TI-84. So between 0 and 2 on this graph, I can see there is an x-intercept. There is a position where this velocity function is equal to 0. So let's use our calculator to find it. So I'm going to hit second trace to pull up the Calc menu to do a calculation. I want to find a 0. That's the second entry. I need to give my left bound, my right bound, and my guess, remember. So I'll be on the left-hand side there. I'll use the cursor keys to move over to the right-hand side of the intercept. And then if you're using your physical calculator, remember you'll do second, trace, entry number 2. I'll do my left bound here. I'll move my right bound over to the other side. And then remember, I have to hit a guess. I can just hit enter a third time and it will tell me my 0 is 1.426. That is, sorry, yes, 1.426. That is what I got on both calculators. That's good. Okay, so that is our final answer. This tells me that TR, that special t value that I wanted to find when my particle was at rest, is, to 3 decimal places, 1.426. Let me close my calculator, and that's us done with that first part of the question. Don't make that mistake like I almost just did, because we also have this second part where we're asked, is the particle moving to the left or to the right? So we need to remember, moving to the left means that the velocity is negative, and moving to the right means my velocity is positive. So when t is less than this value that we found, this 1.426, what was my velocity function doing? Well, you can see it on my physical graph here, right? When I'm to the left of that intersection point with the x-axis, if I pull up the calculator here, you can see it in more detail. Okay, when I'm to the left, when t is less than that 1.4 value, my velocity is positive. So that means I'm moving to the right. Because we were asked to explain, we do need to include that reasoning though. So particle moving to right when t is less than this tr value that I found, since v of t is positive. So how were the points divvied up here? Well, I got 1 point for the correct value here of when we were at rest. And then we got 1 point for saying we were moving to the right, but we did have to have that justification step. Nice job. Okay, part B is asking us all about acceleration and how the particle is speeding up or slowing down. So let's take a look. We want to calculate the acceleration of the particle at time t equals 1.5. So I need to remember that acceleration is the derivative of velocity. Okay, and because we were asked to show work, we do definitely want to make sure we are showing this work. Okay, so well, I could find the derivative of this using my standard differentiation rules, but don't forget, we have a calculator. So we may as well use that, get our correct answer a lot more quickly and a lot less error prone. So let's pull up our calculator again. So let's clear out of our graph window. And now I want to evaluate v prime of 1.5. Now the good news is I still have v stored as my y1 variable. So rather than have to type this in every time I want to do something with v of t, I can just remember, call it my y1 variable. We'll do this several times throughout the course of the question. So we want to calculate a derivative. That's one of our key calculator skills. I am right now assuming that you're fairly comfortable with graphing, solving, finding derivatives and integrals using your calculator. If you're not, I'll put a link in the description to my essential calculator skills video where I run through the 4 key skills that you need to be able to do to be successful on the calculator portions of the AP Calculus exam. Check it out if you're feeling a bit rusty on these, but for now, let's get back to part B of this problem. So I'm going to hit the math menu. I want to calculate a numerical derivative. That's setting number 8. So as I said, I'm going to hit alpha trace to pull up my y variables menu, because then I can select y1 as the function I want to take the derivative of. That is really, really nice. Saves me a lot of time. Saves me from having to enter a complicated function rule over and over each time I want to use it. What is the variable value that I want? Well, it's t equals 1.5. So I'll enter an x value of 1.5 and I will hit enter, and I get this quantity that is very, very, very close to -1. Indeed, if I round that to the decimal places, which is what we should always do, I will get -1 on the nose. So I will get -1.000 as the answer for my acceleration. So we've done the first part of part B. The next portion is asking, is the particle speeding up or slowing down? Well, whenever we see a question like that, speeding up or slowing down, what I need to remember is that's expecting me to compare the signs of the acceleration at the moment in time I'm interested in and the velocity at that same moment in time. Depending on what happens with that comparison of those signs, I'm going to get speeding up or slowing down behavior. So we just figured out that a of 1.5 is -1. So that is negative acceleration. V of 1.5, well, I don't know what that is, but you might remember we already graphed the velocity function, so let's pull that back up. So when I look at my graph, okay, 1.5 is to the right of that x-intercept. Okay, you can see it there. The x-intercept occurred at 1.426, I believe. So t equals 1.5 is slightly to the right. So the velocity function has just dipped below the x-axis. So the long and the short of it is, at this moment in time, the velocity is also negative. So let's put our answer and our reason. So the particle, because the acceleration and velocity have the same sign, the particle is speeding up. So particle is speeding up at t equals 1.5 since a of 1.5 and v of 1.5 have the same sign. Okay. Why is this the case? Well, if we think about the actual motion along the x-axis, okay, at t equals 1.5, my particle, well, the velocity is negative. So I know that I'm heading towards the negative direction, the left, and my acceleration is negative. So the rate of change of velocity is negative, and that's driving the velocity down even more. The velocity is decreasing and becoming even more negative. So I'm already heading in the negative direction, and I'm speeding up in that negative direction. So we're getting sort of faster and faster in that negative direction. You don't need to include that in your answer, certainly. I'm just trying to jog our memory, perhaps, of why this sign comparison is what makes sense for us. So how were the points divided up here? Well, I got 1 point for my calculation of the acceleration, but we needed to show the relationship between A and V prime to get that point. And we got 1 point for our answer of speeding up, as long as we justified by saying acceleration and velocity had the same sign at that moment in time. Nice work. On to part C, which is asking us about the position of the particle. It's telling us at t equals 1, the position of the particle was at -3 on the x-axis, and it wants to know where the particle ends up by t equals 4. Okay, well, this turns out to be a net change theorem in disguise. So let's remember what the net change theorem says. It says in any situation where I know something about a quantity, position, and its rate, velocity, I can use a definite integral to figure out what is changing over an interval of time, over an interval on the x-axis. Something like that, okay? So it says the final value of my function is going to be the initial value, what it started at, plus the net change. Okay, what happened between the start of my time interval and the end of my time interval. So the net change theorem says to figure out that net change, I need to take the integral of a rate. So net change theorem says the final value of my quantity, my position, is going to be my initial value, my initial position, plus the integral of my rate, the integral of my velocity. So let's pin down exactly what we are seeing here. So my final position is going to be x of 4. That is going to be my initial position, x of 1, plus the integral of the rate of change of position. That's my velocity. I need to integrate over the bounds of my time interval. It's t equals 1 up to t equals 4. And then finally, just remember, x of 1 was given to us in the problem as -3. So what I'm going to do is pull up my calculator and calculate this expression using my definite integral calculator. That'll give me the answer. We'll be done. So let's get back to our main window. I know I'm starting at -3. I'm going to add on the definite integrals value. So let's hit the math menu, entry 9. I'm going to put in my bounds, 1 up to 4. Again, I have that velocity function stored under the y1 variable, so I may as well use it. Let me hit alpha, trace, enter y1. You'll select the variable x on your TI-84, and now we'll just hit enter. So, to 3 decimal places, this is negative 2.803. Negative 2.803. That is our final position, our final answer. So how were the points divvied up here? Well, I got 1 point for using that initial value. Okay. Knowing to use that got me 1 point. I also got 1 point for setting up to use the integral, even if I didn't do it correctly. And I get 1 point for the final answer here. Good work. Let's take a look at the last part. Part D, home stretch. Here we're just asked to find the total distance travelled by the particle between t equals 1 and t equals 4. Now this is distance, remember, so it doesn't matter if I'm moving left or right. I want to be calculating that. I want to be counting that in my total distance calculation. So there are a couple of ways to do this, and notice we are being asked to show work, so we will need to justify, back up our calculation somehow. Okay, I'm going to show you the cleanest way to do it. Okay, whenever you're asked for total distance and you know a velocity function, the simplest thing to do is simply do the integral between your bounds, in this case t equals 1 up to t equals 4, of the absolute value of your velocity function. Okay, we have a velocity function. This is a definite integral. We can type it into our calculator, and that will give us the answer. So let's do it. Let's pull up the calculator. Now this is where things can go a little bit hairy, because I don't always remember where the absolute value function lives on my calculator. But that's a good thing to remember. So let's do the math menu. We're going to calculate the definite integral from 1 up to 4 of, I want to do absolute value of velocity. But remember, we have velocity stored as our y1 variable. So if I'm hunting for my absolute value function, function button, and can't find it, I'm going to scour over my buttons and remember, well, it's probably going to be under math, because I'm pretty sure I want to do some math. So if I look along the menu at the top, if I get to num, okay, that's a load of functions to do with number theory. Okay, the very first one is absolute value function. I found it. That is great. And when I select it, the absolute value bars appear. Thank goodness I remembered where it was. I'll then hit alpha, trace, enter my y1 variable again, and then we can just hit enter. And what I get is 0.958 as our final answer. Okay, so how are the points divvied up? Well, we got 1 point for our correct answer, and indeed there was only 1 point up for grabs here, but we did need to show that working. Okay, we did need to show that integral of absolute value of velocity to get that 1 point. Okay, there we have it, another calculator portion of an exam done. If you're doing this in order, we've already tackled the first free response question, and now you're going to be asked to put your calculator away and do parts 3 to 6. If you're following along in order for this exam, I'll put a link to the playlist where I do each of the free response questions in order for the 2024 exam. And as I said, sort of mid-video, if you need to brush up on your calculator skills, here is a link to my 4 essential calculator skills video. If you get those 4 skills mastered, there's literally nothing that they could throw at you in the calculator free response or calculator multiple choice that you wouldn't be able to do. So it's a really good thing to be practicing. Apart from that, thank you for sticking with me, and I look forward to seeing you in the next video. Bye.